Howdy folks, welcome back to another CS 128 honors lecture. Today we're going to be covering ownership and borrowing in Rust. So some goals for today, we're going to review ownership. You learned about ownership with Eustace in the last lecture. Then we're going to talk about transferring ownership and what that looks like in Rust. Then introduce borrowing and go into more detail about that. And then talk about borrowing in relation to data structures like vectors and hash maps. But before that, a couple course announcements. Homework 4 is releasing today. It's due on the 17th at midnight. MP0 is due tomorrow at midnight. And MP1 is releasing today, due on the 23rd, also at midnight. One final announcement. There's been a couple questions about this in the Discord. You can complete Prairie Learn assignments on either of your Prairie Learn accounts, either your CS128 account or your normal Illinois account. Either one works. It will take the highest score across both accounts for every single assignment, so you don't need to worry about which account you're signed into. All right, without further ado, let's get into borrowing and ownership. So with Eustace, you reviewed the three rules of ownership. Each value in Rust has a variable that's called its owner, and there can only be one owner of some piece of data at a time. And so when the owner goes out of scope, that value will be dropped. So let's take a look at what this looks like. Here we have a variable s. S owns this string hello. So when we declare string from hello, variable s enters scope, and again, s owns this string hello. And then we're going to do something with x, whatever it may be. Then we enter a new block of scope, right? And in this block of scope, we're going to declare w, so w enters scope, and w owns this string world. And we again do something with w, and at the end of this block of scope, w is dropped. So this piece of data is dropped from the heap, dropped on the stack, nothing owns it anymore, and w goes out of scope. And then finally, we still have s in scope. S still owns this piece of data hello, and at the end of the main function, s is dropped. And so there are no longer any more owners of this string. S is out of scope, so there are no more owners of this piece of data. Okay, let's look at another example. So we have, again, this string hello, x owns it, but when we try to assign y to this variable x, well, y now owns this string hello. So we transferred ownership of this string hello from x to y by using this let y equals x statement. So x is no longer valid anymore at this point. You cannot use x. So if we tried to print out x, this line would not compile. Again, each value can only have one owner, and we moved ownership of hello from x to y in this line. And so we can no longer print out x, we can no longer use it anywhere in our program. But we can print out y. And so this little line of code will print out hello. Okay, so this sort of brings us into the copy and clone traits. What does this mean? Copy is this sort of feature that is automatically defined for primitive types. It allows you to make these let y equals x statements without having to worry about moving ownership. So we have this variable here, x. X comes into scope. X owns this piece of data 5. And then we have another sort of let statement here. Let y equals x. This is valid because all primitive types are automatically defined with the copy trait. And so the value of x will be copied into y. So y owns a copy of the data in x, and x still has ownership of 5. And so we have two sort of variables, both have ownership of two distinct values of 5. And so we can increment x by 1, and so x will be 6 at this point, y will still be 5, because y copied the data. So when we print this out, this little print statement will print out x equals 6 and y equals 5. So this is different from the clone function, the clone trait rather. The clone is an explicit function call to make a deep copy of some data. So notice in this case, there is no clone function. Primitive types are automatically copied. So you don't need to make any changes to this. You can make let x equals y, or y equals x statements without any method calls, and you will automatically get a deep copy of your data because it's not very expensive. It's a primitive type. Point out the difference between this. Strings move ownership. They're very expensive to copy because you have to go through somewhere in the heap, copy all of the characters, and then return some type of new string object. In this case, you're just sort of copying an integer. That's not cheap at all, and so the copy trait allows you to do that. Let's get more into clone. So once again, clone is an explicit function call to make some deep copy of some data. So what does this mean? Again, when we try to move ownership of a string, we have a string hello, x owns that piece of data, and then we move ownership of x into y. So at this point, this is no longer valid. We can no longer use x, we can no longer modify x because y has ownership of the data. So this will not compile. And you can see that. Borrow of moved value x. So this move occurs because x has type string, which does not implement the copy trait. So there is no automatic copying of string types, and so ownership is moved into y. And then we try to use this value x after the borrow occurred. So we're trying to use, we're trying to borrow x after a move occurred. So we're trying to use x after we moved ownership into y. So this obviously does not work, but we can make an explicit function call to clone to copy data from x into y. So we're making a deep copy of this entire string, and so there's two different hello strings now. X has ownership of one hello, and y has ownership of a separate, distinct hello somewhere else on the heap. And so we can use x after this function call. We can modify it. So we can push world to the end of it. So at the end, this print statement will print hello world, and y will still remain hello. Y is its own string right now. It's completely separate from x because we made this explicit clone function call. So that's the difference between clone and copy. When you want to clone something, when you want to make a deep copy of some expensive object to copy, you have to call this clone function. When you want to make a deep copy of primitive types, you don't need to do anything. Rust will automatically do it for you, as in the case of this unsigned 8-bit integer. This is the case for all types of ints, floats, booleans, characters, tuples of primitive types, that sort of stuff. Okay. So just want to sort of go more again into this example. We move ownership of x into y, so we can no longer use x after that has happened. So the same thing happens in functions. Again, values can only have one owner. So in this example, we have a variable class, and class owns this CS128 honors data. It's somewhere on the heap, and so we can say hello to class. So at this point, we're moving ownership of class into this function, right? Class does not implement the copy trait. Class has to be cloned, and so we're moving ownership from class into this function. So name now owns CS128 honors. Name has ownership over that piece of data, and so then we can use that piece of data to say print hello CS128 honors. And at this point, the value is dropped. Name no longer sort of refers to that data because it goes out of scope, and this one CS128 honors data is dropped from the heap, right? And so when we exit this function call and come back here, this value no longer exists. Name had ownership of it, name went out of scope, and so the value was dropped. And so class no longer is valid because class lost ownership, and so we cannot call this say hello function again. So there has to be a way to fix this, right? Because we may want to call some functions on some pieces of data and perform some computations along the way, but we can't keep just sort of losing access to our data. Well, that's what references are for. So in Rust, an ampersand represents a reference similar to C++, and references allow you to refer to some value without taking ownership of it. They allow you to use it, to look at it, potentially manipulate it. We'll get more into that in a bit, but the original owner does not lose ownership. That's a big distinction. And so we call the act of creating a reference borrowing in Rust. So when you use this ampersand symbol, you are borrowing a value from the owner. So let's sort of fix our examples and see how we can introduce borrowing into our code. So if you're following along in the GitHub, we're in functions.rs in the lecture 6 folder. And so once again, we have this issue here, use of moved value class. Class is moved into say hello in this function. Name takes ownership of this string. Then at the end of this function, right here, name is dropped. And so we lose this data. We can fix that, again, with references. So we're going to say that say hello borrows some string. So we can declare that with just an ampersand before the type. So name is now a reference to a string. And we can declare that we want to borrow a value by calling this function by putting an ampersand in front of the variable we want to borrow. So we're using this ampersand to create a reference to class and hence borrow it. Again, we're going to do the same thing here. So we end up compiling this. There we go. So you can see we print hello CS128 honors twice because we're simply borrowing this variable. And so class still retains ownership at the end of this function. So class still has ownership of this string because we're just simply borrowing it in this function call. Again, if we were to remove this borrow, well, class would lose ownership, and we'd sort of lose the ability to call this function a second time. Okay, let's look at another example. So we have this string hello, right? And we're moving ownership of x into y. And we went over this before. We cannot do this. We can't call this function on x because we've moved ownership of this string to y. So we can make y a reference to this string, right? So we can say ampersand mute. So we'll create a mutable reference to x, and so y is now a mutable reference. We can modify y. Okay, and so we're trying to push this sort of world string to x. And so if you can infer from the last example, we're trying to sort of borrow x here and mutably borrow it because we're, modifying the string, pushing world to the end, but we're getting a compiler error. We have a first mutable borrow here and a second mutable borrow. So we cannot mutably borrow a variable more than once at a time. So what does that mean? Well, there are some rules to borrowing, just like there are to ownership. At any given time, you can either have only one mutable reference to a variable using the ampersand mute operator, or an infinite number of immutable references using the ampersand operator. You can only have one or the other, cannot have both. So either one singular mutable reference or an infinite number of immutable references. And again, you use the ampersand mute operator to get a mutable reference, or just the ampersand operator to get an immutable reference. And so another rule of borrowing, references must always be valid. What does this mean? Well, you can't return references to values, to temporary values inside functions. So if you have a function and you create some type of variable in there, at the end of the function, that variable will go out of scope. So you cannot return a reference to that temporary variable at the end of your function. This is similar to C++. you'll get a sort of bad memory address if you return a reference to a temporary variable. The Rust compiler will prevent you from doing this, so it is there to help you along, but just for you to know, references must always be valid, and you can only have one mutable reference or an infinite number of immutable references. Okay, so revisiting that example, we're trying to create a mutable reference to x, so y is our mutable reference now, and then we're trying to create a second mutable reference when we're trying to mutably borrow x and push this little string to it. So again, this goes against our first rule. We can only have one mutable reference. And so y is that first reference, so we cannot successfully execute this push string function. Okay. I want to talk about ownership in data structures now. This will come in handy in all of the future MPs. So again, I want to reiterate this. Values can only ever have one owner. So what would happen if we try to add elements to a vector? Well, the vector would take ownership of those values. So whenever we push an element to a vector, the vector will own the value and sort of have responsibility of it. And so when we try to access a value from a vector, we're given a reference to it. Remember, the vector owns that value, and so whenever you try to access it, well, you can't take ownership of it from the vector. The vector is going to try and protect its data to be used sort of down the line. So when you try to access data, you're given a reference that you can sort of borrow or mutably borrow. And we'll get into what those distinctions look like in a little bit. So brief example, we have this vector of strings, hello, CS, and 128. And we have this variable element, which is trying to access the second element of the vector. It's trying to access this 128. But we have this error here. And so we're trying to move ownership of 128 outside of the vector and into element. And the vector does not like this. Again, remember, strings do not implement the copy trait. Strings must be cloned. And so element cannot take ownership of this value. We can use the .clone function if we would like a deep copy of the element, but if we wanted to modify the element, well, we have to figure out a different way to do that. So let's get into another example. So here we have a vector of names, so Eustace, Welby, and myself. And so similar to the previous example you saw, we cannot move ownership from the vector into a variable because the vector would like to keep ownership of values. And so we have this vector of names. We can borrow this value using an ampersand operator. So Eustace is now a reference to this first element of the vector, right? But let's say we wanted to modify Eustace. Right? Let's say we wanted to make Eustace a mutable reference to the vector element 0. Well, Rust wouldn't like this because the original variable also has to be mutable, right? The vector has to be mutable in order to be able to change its values. And so we cannot create a mutable reference if the original variable, if the original owner is not mutable. So we can do this by just adding the mute keyword, like you know, before the owner declaration. And so if the owner is mutable, we can make a mutable borrow to that value. And so here, we can put some exclamation marks after Eustace's name and print out this value. So let's see, printing out names 0. So we can run this. And there we go. We mutably borrowed the first element of the vector, pushed a couple exclamation marks to the end, and we're now able to print that. So remember, if you want to make a mutable reference to some value, the owner has to be mutable. Okay. So I want to go over a couple of helpful methods that you'll see a lot in MP1, and these will sort of help you out a lot in any future Rust code you write using vectors. So as you saw in the past example, vector with brackets will try and take ownership of the value. So if you have a vector of primitive types, vector of integers, vector of booleans, vector of floats, this is okay. These types implement the copy trait, and so you're not actually taking ownership, you're copying the value inside that vector at that index, and you have a distinct copy of that value, right? You can use the ampersand operator and bracket notation to immutably borrow the value at index I. And you saw that in the past example. With a vector of strings, strings do not implement the copy trait. So we have to immutably borrow values in a vector using brackets and the ampersand at the beginning. We can also mutably borrow values, as you saw in the past example, using the ampersand and mute keyword. Important thing to note is your vector must be declared as mutable. So you cannot create a mutable reference without having a mutable owner. And another sort of access method is the .get. So .get works similarly to brackets, but it's sort of different in its interface. So again, you'll try to get an immutable reference to the value at index I, but get will return an option. So you'll get an option partially because you can access indices that are out of range of the vector. So if you have a vector of 10 elements and you try to access the element at index 11, that is out of bounds. And so this option will be none. The important thing to note is if you try to use bracket notation and you access an element out of the index range, this code will panic. Your Rust program will immediately exit, and you'll sort of no longer be able to continue. Get is a little bit safer because you'll get back an option, and you can use a match statement, you can use unwrap, all of those option methods that you learned about a couple lectures ago to safely access this vector. Again, so the vector will keep ownership of the value, and you'll get an option type that contains a reference, an immutable reference to the value at that index. If you'd like a mutable reference, you can use the getMute method, and this is similar to .get. You'll get an option type that contains a mutable reference to the value at the index. And so if you have a index out of bounds, your option variant will be none. If you have an index in bounds, you'll get the reference that you request, either immutable with get or mutable with getMute. And again, your vector must be declared as mutable if you want to be able to get a mutable reference to some value. Okay, and so these are a lot of useful methods you'll see in the future. This goes along the vein of the functional programming paradigm in Rust. You'll use these a little bit in the MP, so I want to go over these briefly. So if you want to go over and iterate through the values in a vector, you can use the .iter method. And so you'll iterate over a vector using immutable references. So you'll get a reference to each element in the vector, and you'll be able to do something with it, whether that be printing it out, taking a sum, accumulating it somehow, whatever it may be. And along the same vein, iter_mute iterates over a vector using mutable references. So your vector must be mutable in order for this to work. And then you have vector into iter. This is a very dangerous method. Into iter will try to take ownership of the vector. So there's this concept of iterators in Rust that is more along the functional programming side, but the iterator will try to take ownership of the vector, and the vector will be, so the original variable referring to the vector will no longer be valid after this call to int iter, because the iterator takes ownership of those values, and the original variable is invalid at this point. So I just want to give a big warning. Only use int_iter when you no longer want ownership in your vector. Let's take a look at these iterator methods in our example here. So we've covered mutable references. We have a mutable vector here. Let's try and add exclamation marks to every single name here. So we can say for each name in names.iter, let's start by printing out the names. So print each name out. And comment this out. So we'll sort of get a reference to each name in our vector of names, and we'll print it out as we go through. So here we go. So the first name we got was Eustace, printing that out, and then we got Welby, and then Neil. And again, as you can see in my little Rust analyzer, name is a reference to a string. Okay, so let's try and modify each of these names. Let's see, say name dot push string. And immediately you can see we won't be able to do this because we need a mutable reference to be able to modify these elements of the vector. So we can change this using itermute. And so here we go. Name becomes a mutable reference to a string now. And so we are allowed to push values to the end of, push characters to the end of each value. So if we try and print this out, you'll see that we have modified all of the elements in our vector to now have exclamation marks at the end. So Eustace with more exclamation marks, Welby, 3 exclamation marks, and myself with more exclamation marks. Okay. I want to show what happens with int_iter now. So into iter. So this variable name will take ownership of each value in the vector, right? So it's no longer a mutable reference, it's just the actual value, the string itself. So we can print this out, and you can see, so we'll print out each of the names, but what happens is the vector will no longer be valid. Well, names will no longer be a valid sort of reference to this vector. So if we try to use names here, we can push another name to it. There's Jonah. This code will not compile because we've lost ownership of the names has lost ownership of the vector. And so here we go. We've moved the vector, moved ownership of the vector into this iterator. And so we can no longer access the vector with the variable names. So be very careful with int_iter. Only use it sparingly and try to use simply iter or itermute. Okay, with that, I want to sort of walk through MP1, give you guys a couple hints, and help you guys get started. So, as I said earlier in the lecture, MP1 will release sometime tonight. So by the time you're watching this, you might already see it up in Prairie Learn. So your job in MP1 will be to implement the k-nearest neighbors algorithm. So KNN is used to classify data points by looking at similar data that you've seen in the past. So in this example, we're going to be having you classify different cereal types and sort of predict the manufacturer of a cereal type using some data, the calories, protein, carbohydrates, and fat of some type of cereal. So you'll get a data set of a bunch of cereals, and we'll give you the sort of nutrition quantities of a different cereal and ask you to predict which manufacturer made that cereal. And so what KNN will do is it'll look at all of the data and find the closest point to the point you're trying to predict. So to do that, you'll be using some normalization, z-scores if you're familiar from statistics, in order to do that, you'll need to compute the mean of some data and the standard deviation. And so in this case, you'll be borrowing vectors and iterating over them. You'll do some mutable borrowing for normalization, stuff you've seen in today's lecture. The one new sort of syntax I want to show you guys is structs. We will be covering structs in depth in next week's lectures, but to help you get started, I want to show you some syntax of struct methods. So when you see impl dataset, this function here is use on dataset structs, similar to object-oriented languages like C++ or Java. So when you want to access these variables, matrix and labels inside a impl function, you can get them using the self keyword. So self.matrix will give you this vector of vectors, and you can modify it, use it however you like. And self.labels will give you this vector of strings. So one thing I want to note, you cannot actually modify self.matrix because there is just a immutable borrow to self. So in the future, just look ahead, if you wanted to modify this structure, this struct within a function, you'd have to use a mutable borrow of self. But that is not the case in this example. You do not need to modify the data set. You simply need to just compute some operations upon it and predict given some data. Okay. That is a look ahead at MP1. As always, feel free to reach out to us on Discord. Feel free to come to office hours. We're happy to help. Good luck. Thanks for listening to today's lecture.